So, a couple people now. Anyway, today's topic is going to be thin film. And we're going to be considering a couple of different things here. But anyway, let's imagine that we have light coming in here, bouncing off this top surface. And this part here is going to be the thin film. Most of the time, we can think of this medium up here as being air. And so I'll put air and just say usually, because it's not always the case, but I don't know if I do any examples where it isn't air. And down here will be some other medium, and sometimes it's going to be air. And so I'll call this medium 3 down here. And we can imagine N1 for the index of refraction of this medium. If it's air, it's going to be 1.000. This will be N2, the index of refraction of this thin film, whatever it happens to be. And then we can have an N3 down here, which a lot of times the thin films are put on top of a surface of glass. And in fact, I'll show you wherever I put those binoculars. Here's a pair of binoculars. Nearly all the decent optics you buy are going to have a thin film over the surface. And a lot of times they have thin films over all of the surfaces. And something you can see, I hope, picture here, is that there are a couple of stripes on here that have kind of a greenish hue to them. And they're actually reflections of some white LEDs that I've got up here. And the white LEDs are actually a mixture of colors, but that mixture of colors comes out looking white to your eye, but the film that's on these things kind of preferentially on the lenses on this kind of preferentially reflect green light. And so that's why you see that. I've got some binoculars at school, I think, that have kind of a purplish hue on their thin film. With things like binoculars, it's done to maximize transmission of light through the things and maybe reflect some wavelengths that might be too strongly coming through there. But let's look at how that can happen. I think the eyepieces down here, it's even more obvious that there's a greenish hue to the light that's reflected off of them. So kind of interesting anyway. Okay, and those small binoculars were a whole lot easier to fit under here than some larger ones. But anyway, there'll be light that's reflected off of the top surface here. And since this is air up here and some kind of an index of refraction, there isn't anything with an index of refraction less than air except vacuum. And we're not going to be dealing with vacuums. So this is always going to be greater than N1 as far as its index of refraction. And when light undergoes reflection at a surface where this index of refraction is higher than that one, there will always be a phase change of pi on reflection. And it's like when we had a wave on a stretched string if it reflected off a fixed end, the reflected wave was inverted from the incoming wave. That's what's going on here. If you have a loose end of a string, the reflection that you get at the end of it comes back without that phase change. And we'll have that happening here if, for instance, on the back surface of this thing, if the index refraction of this is less than the index of refraction of this, there'll be no phase change taking place for the light that reflects here. But anyway, we'll continue on. And again, all of the light isn't being reflected. Much of it is being transmitted. And so, and we're not showing any refraction occurring here. And the reason is that we actually want to be considering normal incidence. But if I draw normal incidence, all of these would be lying on top of each other, and we wouldn't be able to analyze it the way I want to. So anyway, this film has the thickness T. There will be a phase change here, a delta phi of pi, and that's for the light that is reflected from that top surface. The stuff that comes into this medium, the thin film, doesn't have a phase change yet. But it's reflected here, and it may or may not have a phase change there. And so that's something that we'll have to learn to consider. But there's certainly going to be a path length difference because the light that comes into the medium has a round trip distance of 2t that it does in here. And so that's going to introduce a path length difference, which will introduce a phase difference. Usually, though, when we've talked about a path length difference, what we've done is used delta for the path length difference. Well, in this case, that's going to be 2t, and we would divide that delta by the wavelength and then multiply it by 2 pi. For every wavelength different, we'll get a phase difference of 2 pi. But in a film that has an index of refraction that is different from 1, the wavelength isn't the same. The wavelength in the film here, lambda film, is going to equal, we'll call it lambda naught divided by, in this case, it'll be divided by N2, the index of refraction of the film. And so we have to worry about that. And this is what we'll have to do with that. And a lot of times we write this as lambda prime, just to distinguish it from ordinary lambda. Well, we'll have two possible phase differences that occur here. We can have a delta phi for the path, and maybe we just call it delta phi for the path, and that will end up being, well, the actual path length difference is 2t, and then I have to divide it by lambda naught divided by n, because that's the wavelength in the path, and then multiply that by 2 pi. Then we can have a delta phi for reflection. And this is something where we have to think carefully. We already have a phase difference that's going on here because of reflection. If we also have a phase change that happens here because of reflection, the only phase difference between the light bounced off the top and the light bounced off the bottom will be due to the path length. But if this one undergoes a phase flip and this one does not, then we have to include that. And so we'll have a delta phi for reflection that will either be 0 or pi. And we have to think carefully about the situation to try and get that right. The total phase difference in general will be delta phi total, and it'll equal that for the path. delta phi for the path, plus delta phi for reflection, which may be 0. And so we need to think all of these problems through carefully when we're looking at this. You've all seen thin film interference before. If you see light reflected off a rain puddle and it's got kind of a rainbowy thing on there, that's thin film reflection. When rain falls on a road, as it flows its way toward a puddle, it picks up oil and petroleum products that are in the surface of the road, partly from car exhaust and partly from the manufacture of asphalt. But it'll pick those things up, and oil and petroleum things have less density than water, and so that thin film of crud floats on top of the water. And when you look at that puddle, you look at it at different angles, and the thickness may not always be the same depending on wind and things like that. But when you look at that at particular directions, you'll see particular colors emphasized in the reflection of the light from that thin film of oil on top of the water. The oil, the top surface of it, will have a higher index of refraction than the air, so there'll be a phase flip here. The oil will have some thickness, and so you get a path length difference there. And when you're viewing it at various angles, the actual path length difference will differ. When we do this formula, we're just assuming it's coming straight down and going straight back out. So we'll always use this. But if it's at an angle, you'd have to be considering that. And so anyway, viewing it at different angles, the path length is different, and different wavelengths will be emphasized in the reflection. So that's why an oil film looks like a rainbow. It's thin film interference. So I've got some things in the classroom. I should have demonstrated them, had you look at them yesterday, but I've just got these square pieces of glass that are pretty flat. But when you hold them in your hand or set them on the tabletop, there's a thin film of air in between those things. And when you look at the reflections of the fluorescent lights in the ceiling, you can see thin film interference happening there. They're not perfectly flat, and so you get some kind of interesting patterns. Anyway, let's go ahead and try to solve some problems using this stuff and see what to do with it. But this is basically the mathematics behind thin film interference. So this one, I didn't get the font size on the wavelength of the light blown up here. It's 5.00 times 10 to the minus 2 nanometers. And so we'll have that. So we've got a material with an index of refraction of 1.30 is used to coat a piece of glass that has an index of refraction of 1.50. So right off the bat, here's something we know. We've got air up here, and here the index of refraction is 1.00. We're not going to have to do anything with that. We've got the film here, and the index of refraction here is 1.30, and we've got glass down here, and it has an index of refraction of 1.50. I'll call it NG and NT for these different things. 1.50. Okay, the light that reflects off of the top surface of this is going to have a phase change of pi, or 180 degrees, but we'll stick with pi as that's usually handy when we're talking about phase changes. Then there'll be the light that comes and bounces off here. And because this has a higher index of refraction of that, this will also undergo a phase change of pi here. So both of these have the phase changes of pi due to reflection. So the total phase difference between the light that's bounced off here and the light that's bounced off here is entirely due to the path length difference. So we can say that delta phi total is just going to be delta phi for the path. Okay, well, if this is the thickness of the thing, I think that's what, oh, we want to know the minimum thickness of this film in order to minimize reflected light at a wavelength of 500 nanometers. So we don't know T in this case, but the delta phi for the path is going to equal 2T, that's the distance traveled, divided by the wavelength in vacuum or air divided by the index of refraction of the thickness, and then times 2 pi. And I can make this a little tidier if I have 2 n sub t times t divided by lambda naught. In fact, this is the way you usually see the formula for it, is delta phi for the path. Okay. Well, that round trip distance can sometimes be, or the round trip distance here, sometimes you can have several wavelengths of light fitting into the thickness, depending on what it happens to be. But in this case, we want the minimum thickness, and we want to minimize reflected light at that wavelength. Okay, lambda naught is going to be 5.00 or 500. Whoops. That's not a -2. It should be a +2. 500 nanometers, I made a typo when I punched that in. In fact, I think I did that on every one of these things. Yep, I did. Anyway, this is in the middle of the visible part of the spectrum, and so I'll have to correct all those. But it's 500 nanometers is the lambda naught. Now, to minimize reflection, this phase difference is going to have to equal pi or 3 pi or 5 pi. Okay? Or, any odd number multiple of pi's is how you get destructive interference. I can't believe I have all of those things wrong, but I do. Yeah, for constructive interference, you'd have to have 0 or 2 pi or 4 pi. That way you get waves adding constructively, but we're going to have the destructive thing going on in this case. Okay, well, the minimum is going to happen when this is equal to pi. So I'll have 2n sub t times the thickness of the film over lambda naught times 2 pi is equal to pi. And kind of interesting thing here, if I divide both sides by 4 pi, I will get t, let's see, times n sub t divided by lambda naught is equal to 1/4. And another way of writing this is t divided by lambda naught divided by n. It's t divided by lambda prime. This is the wavelength of the light in the film. And what this says basically is you get destructive interference if the thickness is 1/4 of the wavelength of the light in the film. Okay, for half of that path, you'd get, actually, you'd be traveling 1/4 of a wavelength. That puts it out of phase by 1/4 of a cycle. And for the return trip, it puts it out of phase by another 1/4 of a cycle. And the total thing ends up being 1/2 of a cycle that it's out of whack by, if that's the case. Something that does pretty much exactly that denominator, or well, it's getting kind of archaic at this point, but the way information was recorded on compact discs was, and still is for that matter, there's a series of pits that are put into the surface of a compact disc. There's actually a film over the top of it to sort of protect this, but there's a laser that shines down at this thing. And some of the time it's reflecting off the top surface. Some of the time it's reflecting partly off the top surface and partly off the bottom of a pit. And when that's the case, if it's the beam width on the thing might actually be something like this. So here's the incoming laser beam, and some of it goes all the way to the bottom and reflects off of there. And they make the depth of these little pits in there a fourth of a wavelength of the light in the medium that they've coated the compact disc with. And that way round trip knocks things out of phase by half a cycle. And when the laser is, say, shining down on something like this, there's a pit and it'll be a maximum reflection. But when it's partly bouncing off of the top and partly bouncing off of the bottom, the intensity of the laser beam that's reflected drops. And maybe when it's at its high point, they record that as a 1. When it hits a pit, record that as a 0 because the amplitude drops. And as the compact disc spins and goes underneath the laser, you get this series of 1s and 0s, and that's how information is recorded digitally, and they transfer that into the amplitude of an electric or amplitude of a current that's sent to your speakers to make noise. So that's how it works. Anyway, it's that fourth of a wavelength difference. So here we want the thickness to be a fourth of the wavelength in the medium, which means the thickness is going to have to be 1/4 of lambda naught divided by the 1.30 that we have there. So we can just plug in the numbers. The wavelength is 500 nanometers. 5.00 times 10 squared nanometers. And we divide that by 4 times 1.30. And we'll get some kind of a reasonable thickness. I'll have to, before I make these ones available to you, I need to fix that signs on those exponents. Okay, I'd get a thickness of 96.2 nanometers. And I've got 3 sig figs here and 3 sig figs here, so I can keep 3 significant figures on this. And that would be a fourth of the wavelength of the light in the thin film. And that way you'll have destructive interference for light of that. That's approximately in the green part of the spectrum. So it's not going to reflect green light well. Okay, here's another one. Let's see what this one is. We've got a soap bubble of index of refraction 1.33, strongly reflects both red and green colors in white light. And what thickness of soap bubble allows this to happen? And they've got the wavelengths, and I need to fix these. The red light would be 7.00 times 10 squared nanometers, and the green light would be 5.00 times 10 squared nanometers, 500 nanometers and 700 nanometers. Visible light goes from 400 to 700 nanometers about. Okay, so we're getting strong reflection in both cases. Now, here's something going on in this case. This is a soap bubble. And so it's the easiest way to draw parallel sides. This is light that's coming down from above. Here's the soap. And it reflects off the top, comes down here, reflects off the bottom. but this is air up here. This is soap here. And index of refraction of the soap bubble is 1.33, which is the index of refraction of water. The soap is usually a small part of the water solution, but we've got air down here as well. So this is a case where there's a phase flip that happens at this top face, but no phase flip that happens at the bottom face. And so we will have a phase difference that we have to include in this case for reflection. And so the delta phi total for the light is going to equal that for the path, delta phi for the path, and there'll be a delta phi for reflection that we have to include here because one of them undergoes reflection and the other one doesn't. Now, we could just subtract off because we know it's a phase change of pi on reflection. We could subtract it away, but adding it does the same thing. And so we're able to go with it. Okay, well, let's see. For strong reflection, we have to have this thing equaling some multiple. Whoops, I don't want to use n 2 pi times m, where m could equal 0 or 1 or 2 or dot, dot, dot. So we can have any of those things happening. Okay. Okay. Yes. Question? Or not? Or did somebody just come on and go live for a second? Anyway, the delta phi for the path is what it's usually been. Delta phi path is equal to 2t divided by lambda naught divided by n for the, well, we've only got that n that we're worried about in this case, and then times 2 pi. And the delta phi that shows up for reflection is going to equal, let's see, that's just pi. And so we get that. Okay, and again, delta phi total, I can write this as, let's see, 2nt over lambda naught times 2 pi and plus another pi. And to get strongly reflected light, this is going to have to equal 2m times pi. And the question is, what thickness of soap bubble allows this to happen? Well, we can actually figure out for both red and green a bunch of different thicknesses and see where they both happen to be the same. So I'm going to make a little table. And in the table, I'll have one thing I'll have is m, and m can be 0 or 1 or 2 and so forth. So we'll see what happens with this thing. And then I'll have a column for green and find thicknesses that will work for that, and also one for red. So let's see how this is going to work out here. If I monkey around with this a bit, actually I could divide everything by pi, and actually 2 pi maybe. I would get, let's see, 2nt over lambda naught plus, oh, actually that'll equal m minus 1. I think that works out okay. Let's see. Let me make sure I did that right. This would be a plus 1. Oh, wait. Not quite. Divide by 2 pi. This would be 1/2. So m minus 1/2 is what's going to happen on there. And so thicknesses that will work are going to be lambda naught over 2n times m minus 1/2. And m, actually, I can't have m being 0 in this case because then I'd get a negative thickness. So m has to be 1 or 2 or 3 and so forth. And so I can set up a calculation here and just kind of do some repetitious stuff. It's going to be end up being 0.5 or 1.5 or whatever the thickness is. So first calculate for green. Green light, the wavelength in the medium is going to be the 500 nanometers. Yeah, 500 nanometers divided by 1.33. So for green light, lambda prime is going to be 376. Whoops. 376 nanometers. And the red light will be something very similar. Yep, want to make sure I do this right. Actually, I might have also divided that by 2, but anyway, for red light, lambda prime is going to be 526 nanometers. Okay, and I can find, okay, I can't have m equals 0, so that doesn't work, but I can have m equal 1. And so I've actually already figured out this part. So if m is 1, I'd have 1 minus 1/2 is 1/2. Yeah, I'll try to set this up. Actually, I think I'll do the trying to figure out the most efficient way of punching this into my calculator. I'll do the red first. 526 divided by 2 times minus 0.5. Okay, so for the first red one, I get about 132, and this is the thickness in nanometers. If I replace that 1 with a 2, I get 395. I replace the 2 with a 3. Get 676. And do the same thing and do a 4. There's probably a smarter way to do this, but I know there is on a TI 84, but this will kind of work for us. 921. And I think every time, actually it's changing by 200 and some odd numbers. I don't feel like figuring that out in my head. I'll stop at 5 though. Hopefully that's enough. Ooh, except I may have to go to 7 for one of them. Just occurred to me 100 and or 1184 nanometers is what it happens to be. 80. All right. Try the same thing for the green. But I replaced 526 with 376. And down here at 5, I'm going to work my way backwards. I get 846, and that's nanometers. That's the thickness. Yeah, I may have had to go beyond this. We'll see. Hundred and 58. It's not going to work. One hundred and 70. I don't think it's gonna work here, but we'll see. Um, 82. Nope. Just for the heck of it, I've got a feeling about this. I'm going to put in 7. N equals 7 into the expression. 122. Nope, that didn't do it. I get 122, or no, 1222. About 1220. Oh, I may have to go farther than that. Let's see. I'll just try the 1 on here. 940. It's farther down the line than I thought it was going to be. Wait a second. 94 is what that is. Yeah, so none of these match up anywhere so far. So let's see. 5 and I thought 5 and 7 would work. Hmm. Yeah, I'm a little surprised they don't match up yet. Yeah, 700, 500. Or maybe I'll try 7 on this one, on the red. No, that shouldn't have done it. Yeah, that would be even more. Unless I made a mistake calculating stuff, which is entirely possible. And 34. Hmm. 6, I get 1034. Yeah, I would have thought if I multiplied this one by a 7 and that one by a 5, that would have made things match up. Maybe I better check that red one again just to make sure. It was 526 nanometers, although actually what I'm going to do hmm. Oh, I went farther than I wanted to. I'm going to recheck a calculation here. I'm not getting any of these to match up. So I think I probably have to go farther, but I'm not sure just where. But that's the procedure that I would use for figuring these things out. I don't see any of these matching up. 676 and 658 are pretty close, but not exact. And they get worse after that. So let me rethink that. I may have to redo that problem. But that would be the method anyway. Strongly reflects both red and green colors in white light. Okay, so I've got to have the total phase difference to be an even or a multiple of 2 pi's. So that was working out. All right, need to rethink it. All right, we'll try something else. A thin layer of liquid methylene iodide, N is 1.756, is sandwiched between 2 flat parallel plates of glass. Well, this is interesting. What must be the thickness of the liquid layer if normally incident light with 600 nanometer wavelength, that time I got the exponent right, is to be strongly reflected? So this one's kind of weird. We've got glass up here. We have oh well, methyhlene iodide here, and then we have glass again. Now, we're not given the index of refraction of the glass, but we know that it's typically around 1.5, something like that, and this is going to be higher. So we have light that comes in here, bounces off this. Okay, this has a higher index of refraction than this does, so there's no phase flip here, but then we're interested in the light that comes into that thin film, which we don't know the thickness of. And there is going to be a phase flip, or no, wait, glass. There is a phase flip here because the glass has a lower index of refraction than the methylene iodide. So phase flip here, or phase, yeah, I'll just call it a phase flip. But no phase flip here because the methylene iodide has a higher index of refraction than the glass. And so let's see, our total phase difference will have delta phi for the path length difference, and one of them undergoes a phase flip. This light undergoes a phase flip. This light does not. So there will be a delta phi for reflection. Okay, so this is the total. And that means it's going to be delta phi total. I'm just going to do a shorthand thing here. I'll have 2n, where this is the index of refraction of the methylene iodide. I'm guessing that's how you pronounce it, times its thickness divided by lambda naught, the wavelength of the light in air or vacuum, plus, whoops, times 2 pi, plus another pi that shows up. And for it to be strongly reflected, we have to have this equaling an integer multiple of pi, and I can write it that way, 2m pi, or an integer multiple of 2 pi. So 2 pi times m, and m can be, in this case, it's going to have to be 1 or 2 or 3 and so forth. So let's go ahead and write this equation again. 2n t over lambda naught times 2 pi plus pi is going to equal 2m pi, or if I subtract pi from each side, I'll end up with 2nt over lambda naught times 2 pi is actually going to equal 2m minus 1 times pi. And then I can divide both sides by 2 pi. I'll come up here for that. I'll get 2nt over lambda naught is going to equal, dividing by pi makes that go away. Dividing by 2 makes this thing into m minus 1/2. And so we have that. And we're after the thickness of the liquid layer for this happening. And it says it's a thin layer. Now we've got a possibility for a bunch of different values of m. And so we can figure out some different ones if we want to. But the thickness is going to equal lambda naught over 2n times m minus 1/2. And m is 1 or 2 or dot, dot, dot. So it could be 1/2 or 3/2 or 5/2. Let's just figure out the 1/2 one. It doesn't say minimum thickness, but that's what we'll calculate. And if we wanted thicker ones, we'd replace 1 with 2 or 3, or we could go up from there. So lambda naught, 600 times 10 squared nanometers divided by 2 times that index of refraction, 1.756, and that's dimensionless. And then for the minimum thickness, we'll just have 1 minus 1/2. And for that minimum thickness, I'd get, in fact, I'm going to punch it into my calculator that way so I can calculate a couple of them. So okay, so for starters, I get 85.4 nanometers. And if I replace the 1 with a let's see, 2, yeah, that's right. I'm just going straight up in numbers here. That's the m value that shows up there. I'd get 256, which is actually 3 times that. And the next one would be 2 minus 1/2. No, 3 minus 1/2, which is 5/2, which is going to be 5 times as much of that. We should be able to do that one in our head. 5 times 85 is 422, I think. We'll see what happens. Nope, I get 427. Oh, there's some change on the back of that I didn't include. Let's see. No, 425. Oops, didn't do it right. Okay, that's where the 427 came from. Okay, I multiplied that by 5 and this by 4. That'll lead to errors. All right, but anyway, there is a series of possible thicknesses for this one. So that works out. I think this problem I'm going to do with a spreadsheet because I'm not trusting myself to punch all these things into a calculator correctly. And I'll redo that and post it. Okay, here's a weird little thing, and it's kind of an indication of the power of dealing with measuring small things using optical methods. And here's what we've got. We've got an air wedge formed between two glass plates. So this is going to be air here. This will be glass, this will be glass. So this is going to have a lower index of refraction of these two pieces of glass, which means the light that reflects off the top of the air barrier in the glass is not going to undergo a phase change, but the light that goes into the air gap and reflects off that bottom one will have a phase change. And so we'll have a phase difference that arises because of reflection, and then we'll also have thickness things going on here too. So when it's illuminated from above by light with a wavelength of 600 nanometers, 30 dark fringes are observed. Calculate the radius of the wire. Okay, well, our delta phi total is going to equal delta phi for a path length difference plus a delta phi for reflection in this case, because the one that reflects off the top of the air gap doesn't have a phase flip, but the one that reflects off the bottom does. And so we'll have that being the case. And this is going to be pi. That one is. This one is going to be 2t divided by lambda naught divided by the index of refraction of the air, but that's 1. So, and then times 2 pi. So in this case, we're going to have just 2t over lambda naught times 2 pi plus pi. And we're interested in dark fringes going on. Okay, so this left side of the equation is going to have to equal an odd number of pi's, which we can get if we have 2m plus 1 times pi here. And m can equal 0 or 1 or 2 dot dot dot. Okay, and eventually we're going to see 30 dark fringes. Now, here's something that's going to happen. For that very first fringe that we have taking or happening here, the thickness of the air gap is going to be essentially 0 at this end. That's kind of a weird concept. Try to wrap yourself around it, but you can see that it's tapering here down there. And so for the first one, you won't fit any wavelengths of light into there. And so this will be the first dark fringe. We'll have this equation will become 0 plus pi. There won't be any path length difference. One of them reflects off the bottom of this glass slab, and the other one penetrates into a very narrow gap of air that's not even a wavelength of light thick. So this thing becomes 0. And for our first value of m, we can have a 0 value, and this will just equal pi. So there's our first dark fringe. It happens when m is equal to 0. We see 30 dark fringes, though, occurring here. So the 30th dark fringe is going to happen when m is equal to 29. Okay, because the first one happens when m is 0. So we'll have m equals 29, and that'll happen when the air gap thickness is equal to the diameter of this wire. Well, we're supposed to calculate the radius, but that's okay. We can figure out the diameter and then divide that by 2. So we'll have 2, and I'm going to just replace the t here with the diameter of the wire. Diameter of the wire divided by lambda naught times 2 pi plus pi is going to equal, let's see, well, if m is equal to 29, I'll have 2 times 29 is 58 plus 1. I'll actually have that equaling 59 pi. Okay, well, if I subtract pi from each side, I end up with 2 times the diameter over lambda naught is going to equal times 2 pi is going to equal 58 pi. Or if I divide both sides by 2 pi, I'll get 2 times the diameter over lambda naught is equal to, the pi's will go away, 58 divided by 2 is 29. Oh, well, that's kind of nice. And so the diameter of the wire here, come up here, is going to equal 29 times lambda naught divided by 2, or we're measuring the diameter of a wire that is only going to be about, what is that, 14.5 times the wavelength of the light. But let's go ahead and plug the numbers in and see what it is. 29 times lambda naught was 600 nanometers. That divided by 2. Okay, and I would get 8.70 times 10 to the third nanometers. And the radius of the wire is going to be half of that. So, I should be able to do that in my head. I get 4.35 times 10 to the third nanometers. So that's a pretty small wire. Actually, that's 4.35 micrometers is what it happens to be, which is, a micrometer is a millionth of a meter. So this is only 4.35 millionths of a meter in radius, or 8.7 millionths of a meter in diameter. So it's a pretty thin wire, is what we have in that case. I think I may stop there, and I'm going to revisit that other problem. But here's another soap film. This one's kind of similar to the previous problem. It's held vertically, so the film drains downward due to gravity and becomes thicker at the bottom than at the top, where the thickness is essentially 0. I mean, this would be kind of apparent with soap, but it turns out glass is also a liquid. And in some of the cathedrals in Europe that were built hundreds of years ago, they were built with some kind of glass in the windows. And if those windows have survived to this time, they'll be definitely thicker at the bottom than they are at the top. And that wasn't the way they were put in. Over time, the glass has flowed down there. And so glass is a really thick liquid. It's one way of looking at it. But you can monkey with that problem. And I'll actually, I'm going to switch to an Excel view and maybe record a solution to that other problem. I'll just keep going here. Let's see. I need to open a spreadsheet over here on the other monitor, and yeah, this will work. I'll just change the view to that. So if you want to hang around, you can, but and I'm in LibreOffice, but this is going to be easy enough to do calculations for. Have a column for M. Actually, I don't have to do that. Should be able to do this. Yeah, I'll just go all 16. Should find something that works. Um, that's the, whoops, nope, 376. Actually, I better recalculate that. Is what I better do. Um, that'd be 500 divided by, it was soap. I'll put it above here. Full sign there. And this is the red, which is 700 divided by, oops, I don't know. I've got a habit of starting with my hand on the J key anyway. Now, are those the same wavelengths I had before? They are. So there's the red. And for this one, I will have it equal this wavelength, which I want to use all the way down. Whoops. Wavelength F4. Oh, shoot. Yes. There we go. Okay. The $ value on there. But I wanted a parenthesis over here. Times. Oh, that isn't where I wanted to put this, but I'll just take that. I wanted to start it here. Okay, I lost it. And I want to keep using the same column, but not the numbers. Okay. -0.5. And I hope I did that right. Yeah. And if I drag this over here. Whoops. Oh, that wasn't what I wanted to have it do. Oh, I wanted to have G2 on this one. Now I should just be able to drag these down and see where they might come out the same. If anything matches up. Oh, I've got too many digits showing on these things. Number. I would show one decimal place. They might be easier that way. Do I get any to match up? Oh, here we go. Um, the 11 and the 8. Okay, that's interesting that they happened there, but um, so when we have, this is the thickness I'm calculating. So if you have a thickness of 1974 nanometers, and that's more sig figs than we can keep, but then you'll get the red and the green both working out like that. So that was higher than I expected them to be. I thought they'd show up at 5 and 7, but they didn't. Anyway, we had to get all the way up to um, n is equal to, or m is equal to 8 for the red and 11 for the green, but it eventually happened. So using Excel made that problem actually doable. Okay, well, I'm gonna stop the recording there and let's see if I can find it here. I don't know why. There we go. Okay, just had a weird little thing. Okay, so I'm stopping.